Welcome to this video on creating the ALU bit. So the ALU bit is in charge of focusing on one bit of output for our ALU. Now remember, we're dealing with 16-bit numbers, so we're going to create one circuit and then place it down 16 times. Now I put I here just as a placeholder for what bit this is going to operate on. So if we place this down and say, okay, you're going to operate on bit 5, then the output coming out would be bus 3 bit 5. And that's basically everywhere you see I gets replaced with 5. So we'll take in bus 2 bit 5 for input, bus 1 bit 5 for input on this one, and then 5 minus 1 it would be 4, and 5 plus 1 would be 6. So we take in bus 1 bit 5 for here, bit 4 for here, and bit 6 for there. And then we'd go ahead and do whatever operation was turned on. We'd calculate the operation and spit out the result. Now also, since we're going to have to do carries, when we add two numbers together, we're going to have to produce a carry out. And the carry out will go into the carry in of the next bit. So when we place this bit 5 down, then the carry in would be from bit 4, and the carry out would go to the carry in of bit 6. So this is the circuit that we're focused on creating in this lab. So this is a basic schematic of what you're going to build in this lab. You're going to need to take your full adder from the previous add and place it down, along with the mux. Now, the first step will be to minimize your full adder. In the lab, it just requires you to do a product of sum or sum of products. You're going to have to do a K-map of the truth tables inside of the full adder and minimize the full adder so that you use as few gates as possible. You also need to do that for the mux. So that's step one, is to minimize your full adder and your mux. Then we have some combinational logic that we need to build over there. I'm going to talk about this first, and then we're going to have some combinational logic that we're going to need to put here and here. And I'll talk about that second, because this circuit, all of this will make more sense once we understand what this logic needs to do. Now, let's first talk about the combination on the right side of our circuit. Now, what we're trying to do is we have 9 different operations that our ALU bit needs to perform. I'm just showing 2 here to get you started, but we do need another 7. So we can add our 2 bits together and put the result of adding them on one of these inputs of this AND gate. Now we're calling this AND gate a pass gate, but it's just a normal AND gate, but the way we're using it as a pass gate. So by shutting these off, we block the result from falling onto the output of the AND gate, because 0 and anything stays 0. So let's say that they want to subtract 2 numbers. So we turn on the pass gate, and now that opens up whatever this is to go into the output of our AND gate, because 1 and whatever that is whatever that is. So if you notice as I toggle it, whatever this is if it's a high voltage, we get the high voltage out. If it's a low voltage, we get a low voltage out. So we're going to have 9 of these pass gates down, and we're going to have an on-off switch for each one of them. So we figure out the result of all 9 of our operations. We put the result on one input to our pass gate. Then the other input becomes the operation that they want to do. So our ALU bit takes in the 9 different operations, and when you flip on one of the operations, say like add, then the result of the add goes through to our output, whatever it is. If it's a 0, it's a 0 here, and it's a 1, it's a 1 here. Now, that relies on all of the other operations to be shut off, because if the result of the add is a 0 and they happen to turn on add and subtract at the same time, the subtract could override it. but we're not going to worry about that in this case. We're just going to go in, we're just going to assume that they will only turn on one of these pass gates as a result. So what we need to do next, after you minimize your adder and your mux, is place down 9 of these pass gates and then do their operations. Now that we know what a pass gate is, let's just take a little break and learn how to use Logisim a little bit more. As you know, these are input switches and these are output switches. So you can see that I put an input switch called Cin onto the Cin input of my adder. Now you might think, how did I get my adder to look like that? Well, you can actually design your own chips. Now that we have our input pins here and our output pins, if you click right here, it'll show you how your circuit will look. Now here is the hard part though. When we click on that, notice down in the bottom corner right here, and it disappears when I move my mouse, but when you click on it, it shows you what pin that belongs to, or what input pin that belongs to. So you can see that that is our bus 3-bit I output, and this is a directional guide right here, so it shows you which way this is rotated. And you can see that one is our C out output pin. And then we have all of our different input pins. Now you might want to rearrange them and make sure that they're in the right spot. Just make sure that you know which pin is which as you rearrange them and maybe label them. Then once you do that, and I'm going to call this main circuit my ALU bit, we can add another circuit onto our thing. We just go up to our menu and we click add circuit, and that's in the project menu. So we can add a circuit, or we can click this button right here to add a circuit. And I'm just going to call this my test circuit. I can grab one of my ALU bits and drop it down, and it will look like however I drew it right there. So you can have a little bit of fun and make your circuits look different if you want. Now, to be honest, that's not what I did for this. Just for speed and making the video, I actually used the built-in mux and adder that come with the library. But you're not allowed to do that. You have to use your mux and your adder to get full points on this assignment. Now, another thing is we can rotate our gates different directions. I can press the up and down arrows, and it's a little bit confusing, but you can just up, down, left, right arrow keys on your keyboard, and you can rotate things around. So I'll rotate my bus input so that the wire is facing down. So now you can see that I have my 3 bus 1 inputs up here, my 1 bus 2 input there, I have my Cin input here, and my 9 operations over here. Now you can always drag your wires across here, and that could get confusing. Now when you drag a wire over another wire, that's totally fine, they're not connected. If you want to connect it, you can drop it onto the wire, and you can see that that actually connects it. But sometimes you can get a really big spaghetti mess of wires that can be really hard and confusing to debug. So Logisim, to help you avoid that, it's trying to be as nice as possible as you design your circuit, has what's called a label or a tunnel inside of it. So you can grab this tunnel here, and then inside of the tunnel, you can name it whatever you want. So I'm going to name this tunnel add. It's okay to use the same name that you gave the switch or a different name. It doesn't matter. But what is important is we can grab another tunnel and drag it over here and label that the same thing, add. And now that as long as they're the same case, it's like variable names in programming, as long as they match, then we basically connected this wire up to that wire. So that's a nice little way, and they call it a tunnel because our microchips are layered, and we're able to take a wire down into a couple layers, tunnel it over, and then bring it back up in some other spot. So once again, when on the right side of this logic, we're going to have these 9 pass gates. So you can see I took my OR gate and made the number of inputs 9 so that we can hook up 9 pass gates to it. Now, I'm going to go ahead and connect the subtract up and the 2's complement. Now, one cool trick with these tunnels is you can grab one, hit copy, or hold down Control C or Command C if you're on a Mac, and then Command V to paste it. So you copy and paste that tunnel. Then you can drag it over, use your arrow keys to orient it the right way. So I press the right arrow to get it to flip around that way. And that's a nice, easy way. You don't have to worry about making sure you type the right word. So whoever's going to use my ALU bit will come along and turn on whatever operation they want. They say they want to subtract. If you notice, that turns on this pass gate right here, and then whatever the answer for subtract is will fall through to my output. So that's how this is going to work. So you need to put down, and I put down 3 of the operations, add, subtract, and 2's complement. You need to put down another 6 of these pass gates. Now you don't have to actually label them pass gates. I'm just doing that for this video. Now I'm going to show you what to do for and then briefly describe the next few operations. But all of this information is in your lab write-up. So and means we want to do a bitwise and between bus 1 and bus 2. So I could grab an AND gate, place it down. By the way, if you like it to be smaller, you could go to narrow. And this only needs to be a 2-input AND gate. And we're going to AND bus 1 and bus 2 together. To avoid the spaghetti, I'm just going to add some tunnels to those. And I'm going to just call this bus 1 bit I, and another tunnel for bus 2 bit I. All right, and then we'll just go ahead and copy and paste these tunnels, and we'll AND these 2 operations together. I'm going to put it over here a little bit more. By the way, if you feel like you're running out of room, just zoom out and you can have lots of room. You can highlight everything. You can drag certain things, certain places. Just make sure you're always making constant backups of your work so that if anything happens that messes everything up, you can go back to a backup. Also, there's also undo. Hold down Control Z or Command Z to be able to undo your work. So there's bus 1 connected. I'm going to connect bus 2. So remember the AND operation wants to do a bitwise AND between bus 1 and bus 2. So we use an AND gate to do that. And then we grab a pass gate. Again, a pass gate is just an AND gate. So here's the result of ANDing bus 1 and bus 2 together. I'm going to take that result and put it in as one of my outputs to bus 3. Now it might get really crowded in here, so just move this guy over to give yourself more room. Then the operation, we're always going to calculate the AND of bus 1 and bus 2 together, but we're not going to spit the output out unless somebody activates this pass gate by putting a high voltage on this wire. And how they would do that was they would connect our input AND, meaning they want this ALU bit to perform the AND operation. And if they connect that AND operation over here, then if they want bus 1 and bus 2 ANDed together, they'll turn that one on. And you can see the result of ANDing bus 1 and bus 2 together goes out to the output. Now let's say they don't want AND. Instead, they want some other operation. So notice bus 1 and bus 2 are still ANDed together, but the pass gate is blocking the output from reaching here. So that way, only the operation they turn on will go out to our output. So they can choose one of these 9 operations that'll activate one of the pass gates that'll allow the output to go out. First, let me just go over what these operations. This is a bitwise OR. So it's going to look like a lot like this, but with an OR gate right here. And then this is a bitwise NOT of bus 2. So we just grab a NOT gate down and put the output of the NOT gate onto the pass gate for the NOT operation. Shift left, if we're shifting our number to the left, that means bit 4 gets shifted up to bit 5. So if we're bit 5, we want bus 1 bit 4 to become our output. So all we need is a pass gate with this connected to it and shift left. Shift right is going to use this input right here as its output. And then TRA1 is really the simplest operation. We just want to take whatever is on bus 1 and put it to our output. So again, just a pass gate. This connects to activate the pass gate, and bus 1 is the right answer that we want out for our output. So those are all of your operations. You could go ahead and build the rest of this circuitry, pause the video, come back, and then we're going to learn, we're still need to complete our add, subtract, and two's complement operations. So the add, subtract, and two's complement operations are going to take advantage of the full adder that you created in the previous lab. Now you could put down 3 full adders, one for add, one for subtract, and one for two's complement, but remember we're still trying to use the minimum number of gates. And we can use fewer gates if we kind of configure this adder so that when we want to add, it will add bus 1 and bus 2 together. And when we want to subtract, it'll subtract bus 1 and bus 2 together. And when we want to take the 2's complement, it'll take the 2's complement of bus 2. So remember when we add, so by default, we want this guy to add. So what this mux does is it's kind of like a digital switch that can choose whether we want input A to go to our output, or if we want input B to go to our output. If you notice, the A and B inputs are bus 2, but the B input goes through a NOT gate, so it gets inverted. So remember how you add, or how we learned how to add? We take the original input, and then we add the 2's complement of the second number. So the 2's complement is achieved by negating all the numbers, and then adding 1, but only to the least significant bit. So when we want to subtract 2 numbers, we take our first number and we add the negative version of our second number. To negate this, we invert all the bits, but we only want to add 1 to the least significant bit. We don't want to add 1 to all of them. So what we're going to do in this lab is negate all the bits, and we'll worry about adding 1 to the least significant bit when we connect all 16 of them up together. So when we deal with a single bit and we turn on subtract, we're going to invert all of the bits of bus 2, but we're not going to add 1 to any of them because we don't know which bit we might be. We might be the least significant bit, but we also might be any of the other 15 bits. So since we're making a generic circuit that can add any of the bits together, we're going to add the 1 in the next lab. So by default, our adder is going to add bus 1 and bus 2 together, and then the output will go on into this logic that you've hopefully already built. The add switch will be turned on, which will turn on the pass gate and allow the output of this adder to go into bus 3. But when we turn on subtract, what we want is this switch to flip so that the negated version of bus 2 goes into our adder. And in fact, when we turn on 2's complement, we also want to negate bus 2 because we're going to use the same NOT gate on both the subtract and the 2's complement. So for this input right here, it needs to be a high voltage when we are subtracting or taking the 2's complement. So we want it to be high, and it should be a low voltage on any other operation. Okay. Now you can draw up, and what you should do is maybe draw up a truth table and go ahead and figure out a Boolean logic expression that has inputs for subtracting 2's complement, and when they're on, you want this to be a high voltage. Although you might not need to draw up a truth table because the logic is really simple. When we're subtracting or taking a 2's complement, make this voltage go high. So again, just think that through. When we're subtracting or taking a 2's complement, then have this voltage go high. So there's a little hint for you to figure out this one. It's actually pretty easy. Now we also need a little bit of logic on this input. We don't want to connect bus 1 directly because when we're taking the 2's complement, we actually don't want to add in bus 1. We just want to take bus 2 and have it be the output. Now, the reason why we're using the full adder is because when we add 1, we're going to need that carry in and carry out functionality. So we still need to use the adder, but we want to make sure that when we are taking the 2's complement of bus 2, that we're adding it to 0, not bus 1. So you can come up with another truth table for the A input of bus 1. So the truth table will take in as inputs bus 1 bit I and 2's complement. And when 2's complement is on, we want our A input to be 0 no matter what bus 1 says it is. If 2's complement is off, we want whatever bus 1 is. So if it's off, we want this one to be a 0. And if it's off here, then we want this one to be a 1 because bus 1 is 1. However, when you're taking the 2's complement, we don't want to add bus 1 in at all, so we always want 0 to be our output. That way, when they turn on their operation, this adder, combined with the mux and the logic that you added here, can switch from adding the numbers together, subtracting the numbers together, or taking the 2's complement by feeding in a 0 for this A input. Well, now the sum will come out, and as you saw in the previous circuit, it will split and go to the 3 pass gates for each one of those operations, and that will have then go out to your output. So after you've done all of that, you'll want to draw your circuit so that it looks nice, because remember, in the next lab, you're going to have to place 16 of them down. So now how do you pass off your circuit? What you need to do is create a screencast, and you're going to first show your circuit. And as you show your circuit, explain how you figured out the right result for each one of your 9 different operations. After you've explained that, then what you want to do is show how you drew your circuit to make it look nice so that it's more functional in the next lab. Then go down to add a new circuit to your lab. And as you add the new circuit, place your ALU bit down, hook it up to some switches and some outputs. So take some outputs and hook it up to all of your different outputs. So you're going to have the C or the bus 3 and the C out output. So go ahead and hook those up, and then hook switches up to all of your different inputs, and then just quickly test out a couple operations, like your add operation. Can you add bus 1 and bus 2 together? Can you add bus 2 and bus 3 together? And so on. Now you don't need to spend a lot of time on that. Just don't make a video of you hooking everything up. Just make a video of you showing this circuit, explaining that. Then show this circuit right here with all the switches hooked up. Don't make a video of you hooking up the switches. Grab your poke tool that allows you to change the values of the switches, and go ahead and show me that a few of your operations work. Try to keep this part to about 30 seconds. As far as explaining this part of your circuit, try to keep it to about 2 minutes, and hopefully that will show that you have completed your ALU bit.